So let's talk about the rate for a zero order reaction. So for a zero order reaction, the rate is constant. Let's write the rate form out. So the rate form is rate equals to k raised to power b, the concentration of b raised to power 0, because the order is 0. So it can also be written as change in concentration of b over the t. So the rate constant is the rate is constant. It does not change with the concentration as it does for a first order reaction. Remember that anything that is raised to power 0 is 1. So the rate is the same thing as the rate constant. So for us to derive the rate equation for a zero order reaction, we need to multiply through by the t and divide both sides by the concentration of b raised to power 0. So it's the same thing as, okay, let's write it out. So we have that um, negative the b over the t. So we have the t over uh, b raised to power 0 equals to k b raised to power 0, and then we have the t over b raised to power 0. So this cancels this, and this also cancels this. So n to the raised to power 0 is also 1, but I just want to simplify it. That's why we have been writing that. So we have that changing concentration of b over um, b raised to power 0 equals to k dt. So let's multiply negative. Let's put this negative here by multiplying through by negative 1. So we have changing concentration of b over b raised to power 0 equals to minus k dt. So let's take the let's integrate both sides. So we have that x equals to 0, x equals to x, and then we have that the b over concentration of b equals to, we have 0 and we have t here, so we have that negative k dt. So we can therefore say that this one becomes um, so we have that b, when we integrate that we have b, so we have this, and therefore we have that minus k t t and 0. So from there we can see that bx minus b naught equals to negative kt plus k times 0. So we can therefore say that bx minus b naught equals to negative kt. So we can rewrite this as bx equals to negative kt plus b naught. So this can also be written as this: b minus x, which is the final concentration, equals to negative kt plus uh, b. So this is the initial concentration of the reactant, and this is the final concentration of the reactant. So this is the zero order kinetics for a zero order rate law. So we have this equation here. So let's talk about the units of the rate constant, and let's also talk about the straight line graph for this equation. So a plot of this against this should give a slope, should give a should give this slope. So what I'm trying to say is this: m equals to mx plus c. So our y-axis is b minus x, our x-axis is what is time. So our gradient or the slope is the same thing as negative of the rate constant, and our intercept is b. So the units of rate constant, units of k for zero order reaction, Recall that the rate for a zero order reaction is the same thing as this. So recall also that the unit of rate is the same thing as molar per second. So we have that K equals to this raised to power 0. So anything raised to power 0 is 1. So we can see that the unit of K is the same thing as molar per second. So which is also the same thing as mole dm cube s minus 1. So that's the unit for zero order reaction. So let's talk about the half-life for a zero order kinetics. So recall that this is the equation. So we can say that b minus x equals to negative kt plus b. So at half-life, we have that our b minus x becomes b over 2. Therefore, we can say that uh, b over 2 equals to negative kt half-life plus b. So let's collect like times. We have that b over 2 minus b over 1 equals to negative k half-life. So we have over 2, and therefore we have that b minus 2b equals to negative kt half-life. So we have that negative b over 2 equals to negative half-life. It cancels this, and therefore we have that half-life for a zero order reaction becomes b over 2k. So this is the initial concentration. So this is the rate constant. So here is a simple chart that you may want to screenshot. So just pause and screenshot this. So this is zero order reaction, first order reaction, and second order reaction. So the rate law for a zero order reaction is this. Rate law for a first order reaction is this, and this for a second order reaction. So in the integrated rate law, it's also written out here. So the plot needed for a straight line graph, remember that this is the same thing as y equals to mx plus c. So our y is this, our x axis is also this. So we also do the same thing for the remaining order there. So you already know how to calculate the half-life for each of them. So pause the video and screenshot this. Try to understand what is here.